Okay, everybody. Thank you for joining us today for our very special Hurt-Lindy colloquium. This is a very special lecture. It's actually called the PH lecture, and it's an endowed lecture established by the Hurt-Lindy family of California. And Dr. Hurt-Lindy is an alumni member of the Smithsonian National Board, and for several years he served as its official liaison to SAO. The family established the lecture to encourage and to celebrate the observatory's outstanding young scientists. And there's a large list of past lecturers, and it includes people like Laura Kreidberg, our own Sean Andrews, Karen Oberg, Mercedes, Lopez Morales, and also Gaspar Bakos. Now, today I'm delighted to welcome Richard Teague. Richard is a native of the UK, and he studied for his astrophysics MPhys at University of Edinburgh before moving to Heidelberg to study for his PhD at the Max Planck Institute there. His thesis was on tracing the earlier stages of planet formation through modelling and sub-millimetre observations. And after graduating, he moved to the University of Michigan, and that was for a postdoctoral position, followed by coming to the CFA as an SMA fellow. During this time here, he worked. He was focusing on developing new techniques to detect young planets that are still in the process of forming, and with these methodologies, laying the groundwork for the award of a large observing program on ALMA to conduct the first campaign to find still-formed embedded exoplanets. Richard's currently and just very recently become an assistant professor in the Department of Earth, Atmosphere and Planetary Sciences at MIT. It's a pleasure to introduce Richard for the Hurt-Lindy lecture. I want to thank the Hurt-Lindys for their sponsorship and support of the observatory, very generous, which has been really helpful in to be able to support all of these long list of fantastic junior scientists. And Richard today is going to be telling us about a 6D view of planet formation. Thank you, Richard.
Works. Is that coming up? There we go. So, hello everyone. Thank you very much for the introduction, Lisa. And I just want to echo the thanks to the Hurt-Lindy family for supporting this lecture series and giving me the opportunity to talk to you today. Before I dive into talking about the science, I want to just acknowledge that astronomy is really a collaborative science, and that's one where we make the best progress, where we get to work with different people with different points of view and sort of discuss the scientific problems that we're facing. So with that in mind, it's really been a privilege and an honor to work at a place like the CFA for 3 years, where I've managed to make those connections and work with a whole variety of researchers, both at the senior research level, postdocs, excellent graduate students, and undergraduate students. So a lot of the work that I'm going to show you today has really been thanks to making those connections at a place like the CFA, and so my time here has really been a special one. So I want to talk about what I've been doing, and that is trying to work towards a 6-dimensional view of planet formation. So by 6 dimensions, I'm talking here about the 3 spatial dimensions and the 3 kinematic dimensions. We really want to understand how planets are forming. And the eagle-eyed ones of you will realize that this picture I've got on my title slide isn't actually a planet. This is a moon, one of Saturn's moons embedded in the rings. But I think this is a really nice picture that sort of shows a lot of the concepts that we're trying to understand and observe in protoplanetary disk and trying to see where planets are forming. So I'm thinking here about the idea that we've got a large body that's perturbing dust distributions, carving out gaps in rings. It's driving these interesting sort of dynamical features that even have a three-dimensional component to them. So you're seeing shadows on them. And I think this is a really nice analogy for what we're trying to do at much distant scales when it comes to understanding planet formation. Now, whenever you talk about planet formation or exoplanets, you really want to start with the fact that we're in a really incredible time with just the number of exoplanets that we know. 30 years ago, we only really knew about the planets with our own solar system. And so that's what I've plotted here as a function of their mass on the y-axis relative to their distance from the star, the host star, on the x-axis. And so over the last 30 years, we've seen a huge increase in the number of planets that we've detected, thanks to an incredible amount of development with terms of instrumentation, new data analysis techniques, and simply just a number of people working in the field really spending a lot of time trying to dig out these exoplanetary signals there. And so now we're in a regime where we know something like 5,000 extrasolar planets and a similar number of them waiting to be confirmed. And these sort of results have shown these really incredible demographics here, where we're probing a completely different area in the parameter space looking at these planets. We're looking at ones that are much closer into their host star than anything that we see in our own solar system, and also a lot more massive ones. And while the study of this sort of demographic population is something that's incredibly broad and you can spend a whole hour talking about, in terms of planet formation, there's two facts that I want you to take away from this. Firstly, it appears that planet formation has to be a robust process. We can say with statistical certainty that every star, on average in the Milky Way, has at least one planet. So therefore, we need a formation mechanism that is going to be robust to the sort of initial conditions. We're going to be seeing this everywhere. We can also see that this process also has to provide sort of a huge variety of different planetary types. It's not going to just be enough to explain our own solar system, but we've got to find a planetary formation process that can explain all these different planets as well. So this is quite a tough challenge. But I think what's often missed in these sort of introductions is it's not just these exoplanets where we've seen a huge improvement in our understanding. The last 30 years has seen an incredible improvement in our understanding of planets close to us, those within our solar system. So this is by sending probes such as Cassini and Juno to some of those gas giants and really studying these things in detail. So this is just a stylized video of one of Juno's flybys of Jupiter to just give you a sense of the detail of these sort of planets that we can probe. And so we can understand things like their gravitational moments and get insights on their cores and internal structures. We can look at the compositions of their atmospheres. And I think what's even more incredible, and something that's fairly unique in astronomy, is that for planetary bodies, we can actually go to them, obtain samples, and then bring them back to Earth. So this is just a little movie of NASA's recent probe OSIRIS-REx, which has gone to an asteroid named Bennu, and it's landed on the surface of the asteroid, collected some samples, and it's now returning back to Earth so we can analyze these sort of dust particles in laboratories here. So that's expected to arrive back on Earth in roughly a year's time, late in September 2023. And this is really providing us a sort of a unique lens at what planetary bodies are made of. So we have these two aspects. We're looking at one side, the very large demographics of what exoplanet populations look like, but at the same time, we've also got these wonderful details about the objects in our own solar system. So while we're in a lovely place to think about the amount of data we have to hand, this really means we have to think about how we're going to start solving these questions. So we want to understand about where these planets are forming. When I say where, I mean how close to the star are they forming? To see this diversity in the distance, is this something that they're intrinsically born with, or is this something that evolves later throughout their life? What are the mechanisms that are driving planet formation? Is it really realistic to think that the same mechanism is forming these really massive super Jupiter planets at large separations from the star, compared to these very small rocky terrestrial planets like Mercury in our own solar system? And finally, what materials do these planets form from? We know from our own solar system we can go and look at the composition of these bodies, and now with things like the James Webb Space Telescope, we're starting to really have a detailed picture of what's in the atmosphere of some of these exoplanets. Do they all seem to have the same composition? Do we expect all planetary systems to be formed from the same starting set of materials, or are we going to see a similar diversity in those as well? So the way that I want to answer these questions is to try and understand or witness the planet formation process firsthand. And this means going to systems where we know there are stars forming, because essentially planet formation is a byproduct of star formation. This is showing a wonderful image of a recently formed star, and you can see up in the top left there, it's formed right in the center of that, and it's enshrouded by this cloud of gas and dust. Because this gas and dust has some angular momentum, it can't directly collapse onto that newly formed star, and instead it has to form a disk around it. And it's from this disk that we believe planets are formed. So when we zoom into this star and look at it at slightly longer wavelengths, we see something like this. So this is HL Tau, and I'm sure this is an image that is familiar to many people here. This is a really famous image because this was the first one to really show that in the dust around these new stars, we see all this incredible structure, these gaps and rings. So if you think back to the title slide where we have this moon and Saturn's rings opening up gaps in the dust, what we're thinking is happening is very similar here, that we have young, recently formed planets carving out gaps in these dusty rings. Now, when this image came along, this was very exciting because it looks like, yes, we've now got real evidence that we're tracing the earlier stages of planet formation. But we didn't know whether we were just lucky. Was it just chance that the first thing we looked at with this resolution happened to have the rings that we were hoping for? Or is this a common feature? And so really, Sean was the one that set off and answer this, conducting the D-Sharp survey. So this was one of the first large programs that ALMA commissioned. And this was set out to really answer the question of how ubiquitous these substructures are. And you can see from this gallery of disks that the answer is that these structures are common. Essentially, wherever we're looking, if we have enough spatial resolution and sensitivity, we're going to be seeing features in the dust around these young stars. And so this is really exciting. It means that even if these are not all related to planets, the fact that we know planet formation has to be so ubiquitous and everywhere in the galaxy is really likely to expect that at least some of these features that we're seeing here have to be related to the planets. And so I'm going to talk a little bit later about how we think we can go beyond simply looking at the dust and actually detect where these planets are in these systems. But before I move on to that, I want to talk a little bit about the structure of the disk, because this is really something that we've made tremendous headway in the last couple of years, and this is something that's really helping us understand a lot better what processes could be around that are actually forming these planets. So in this image, there's actually another source that really nicely shows what we're dealing with here, and that's down here in the bottom right, this HH30 object. And you can see this is a HST image of it, and I want you to take away 2 points from this figure. Firstly, you can see that these disks are vertically extended. So while that disk of dust that I showed you earlier of HR tau seems to be very flat and planar, here you can see that for an edge-on disk, you definitely have some vertical extension to it, with the dusty midplane blocking out the light there. You can also see that it's dynamic. It's firing a jet along its axis. So that means that these disks are not quiescent places. There's something within the disk that's allowing us to transport angular momentum and material through the disk, moving that material closer to the star to regions where it can get launched as a jet or in some cases a wind. And so these are very active places, and really this is all pointing towards a perfect scenario for looking at looking for the planet formation process. So this is a very sort of unexpected result, but I think this is something over the last couple of years that we've really had to embrace in understanding protoplanetary disks. And this is the idea that they are not flat, but they're 3D structures. This added dimension that we're seeing has been both a help and a hindrance. So you can imagine that whenever you're doing modeling, if you're adding in a third dimension to that, that's going to make things a lot more complicated. You've got a lot more flexibility, and that's really a tough thing to take account of. But on the other hand, having this extra dimension is really helping us understand a lot of different things. In particular, when we're looking at the different dynamical processes that we think are powering planet formation, their vertical dependence is allowing us to distinguish between them in ways that we couldn't have done if the disks were two-dimensional. So this is just an image of IM loop. This is taken with the sphere instrument on VLT, and what you're seeing here is the scattered light of the small submicron grains high up in the atmosphere. These are the small grains that are very well coupled to the gas and so easily lofted up higher. But when these grains collide and stick and start to grow, sort of the beginnings of planet formation, they decouple from the gas. They're no longer able to be lifted high up into the atmosphere, and they start to sediment out to the midplane. So you can see down here that the larger grains are going to move to this thin disk you've seen before. So looking at slightly longer wavelengths that are more sensitive to these larger grains, you see, again, a very different image of the disk. Here, it's completely flat, and you also see a lot more structure in the disk than you do necessarily on the surface. And this, again, is a very promising point, because if we think there are planets forming in this disk, then they're going to be forming in the midplane, perturbing those grains, rather than necessarily propagating those perturbations all the way to the surface. So in general, when we think about the dust in a protoplanetary disk, we generally think that the millimeter grains are always stuck in the midplane and tracing this thin 2D disk, whereas the submicron grains, closer to ISM-style grains, are lofted high up and kept in the surface of the disk. But of course, it's not just the grains that are in these disks, it's actually the gas as well, and it's the gas that's allowing these grains to get lofted so high. And there was this work by Christophe Punt that really laid out the method that we now use to trace the same emission heights, but for molecular emission in these disks. And so this is an image of PDS-70, a well-studied protoplanetary disk, because it's the only one where, or one of the first ones that we detected planets in. And these contours on this image are trying to show the 3D surface that we've extracted for this. So following this method from Christophe, we're able to see how high, from how high above the midplane, this CO emission is arising. And for this particular disk, you can see that there's a large cavity in the center, and then you have this large flaring structure outside that looks a bit like a donut or a bagel. And so we can start to really probe the 3D structure of the planet formation environment by looking at the distribution of the gas and the dust in these systems. And we've been able to really apply this to a whole variety of different sources. So this is some recent work by Charles Law, who's a graduate student here at the CFA, where he's been applying these techniques to the sample of disks that we have sort of suitable data for. And this is just a summary of the 16 disks that he's applied it to. And you can see that not only do they have different orientations on the sky, which you should expect, it should be a random distribution, but they're all showing the same sort of flared structure. So in itself, again, this is not really a surprising result, but it's really reassuring to see that disks do look exactly like we had predict them from the analytical models. And what's interesting is now that we start to have a sample of them, we can start to understand whether there's any correlations between the shapes and structures of these disks in 3 dimensions to any other properties of their host stars. And so at the moment, there doesn't seem to be any big relationship, but the only real correlation Charles was able to find was between the size of the disk, which we've characterized by this RCO value, and the average vertical extent of the disk here. So essentially what we're saying is that the larger the disk is, the more radially extended it is, the more vertically extended that is. So that essentially means that these disks are all flaring, and so the larger you have the disk, it means it can extend to higher heights. And I think this has really strong implications because it allows us to study the density structure of these disks. Before, we really didn't have any way to understand how the gas is distributed along that vertical column. But by looking at these sort of correlations, by tracing the vertical sort of emission height of these molecules, is really going to grant us access to understanding the 3-dimensional density structure of these disks. And that's going to be a crucial part or input to these models of planet formation. When we talk about the 3D structure, it's not necessarily just the vertical extent of the disk as well. We know that these disks can be warped and torqued by things like binaries in the center. And so these are some results from this really wonderful work by Alexander Bohn, who's a recent graduate of Leiden. And in this work, he was using VLT gravity to look at the orientation of the inner regions of the protoplanetary disk and comparing that to the outer regions of the protoplanetary disk. We wanted to understand whether they were relatively all aligned or whether there was some misalignment in there in terms of having a warp or a broken disk. And this is a really important question because we know there are some planets that have orbits that are misaligned relative to the sort of orbital plane. And we want to know whether those formed from a warped or misaligned disk, or whether they actually formed within a plane and then there was some other dynamical process that inclined their orbits relative to the other planets. And so the finding of this was really that, firstly, this is an incredibly challenging measurement to make. Trying to measure the orientation of these disks, the inner disks, is a really hard thing to do because they're just so faint. But on average, Alexander found that the inner inclination, which I'm showing on the left column here, for the inner disk, shown on the x-axis, is slightly higher than the inclination that we found for the outer disk. So in general, there was a sort of a small, moderate warp for most of the disks that we found, although it's very hard to quantify whether this is a significant deviation or whether there's just big uncertainties here. As I say, this is a very sort of new direction that we're pushing in, and I think with the advancement of our understanding of how gravity is working, the understanding of the inner disk, is really going to help us understand this connection between the outer disk that we trace with ALMA and the inner disk where we've got terrestrial planet formation happening. It's not just by directly measuring the properties of the inner disk that we also can learn something about what's going on close to the star. We can also look for shadows. And I think this is really most nicely shown by this work looking at HD 142527 by Seba Marino, where they saw these really striking shadows in their continuum emission, shown on the left here. So you can see that there's two wedges cut out of that continuum emission. And in this work, they showed that you could explain this away by having a misaligned inner disk that was casting a shadow on this outer disk that we're seeing. So this schematic on the right is not to scale, but just to show how a misaligned inner disk is going to cast these shadows along a particular axis. And this panel over here is showing you their model where they ran radiative transfers of this to show that you can really get a wonderful match to the observations with this sort of very simplistic picture. And so this is a really, I think, a powerful tool. We're seeing this in a lot of systems. If we look at the light curves of the stars, we can see this sort of variability that's likely due to circumstellar material orbiting around it. But I think what's particularly interesting is that when we take this technique and then apply it to the gas as well, rather than just looking at the dust. So this is some recent results where we've been looking at a disk TW Hydra, and this map on the left is trying to show the residual in the background average integrated intensity. So here you can see that on one half of the disk we have a predominantly negative residual, and on the right-hand side we have a predominantly positive residual. And so these are very subtle deviations. In terms of gas temperature, this equates to something like 2 to 3 Kelvin. So these are incredibly sensitive measurements that we're making here. But we do see this sort of persistent asymmetry in the residual. And interestingly, this aligns exactly, or not exactly as you'll see, but very closely to shadows that we've seen in the dust traced by the Hubble Space Telescope. So there's been a whole series of observations of this disk, because it's a very famous one, looking at the scattered light, so in the optical. And there's been a shadow that's been traced, and it's been seen and observed to move around the disk with a certain periodicity. So on this panel, I'm trying to show at the top how the shadow changes shape through time. So on the x-axis, we have the polar direction and then the radius. So in some epochs, you have a very straight shadow, so it's just going radially outwards. And in some epochs, you have a really strong bend in the shadow, so it's curved around. And then on the bottom panel, I'm showing you roughly the position angle that these shadows appear on the disk. So as a function of time on the x-axis, and then position angle on the right. And so you can see these 6 boxed measurements, and unfortunately their periods or their sampling is taken such that you can't really distinguish either between a constant angular rotation around the star, so something that perhaps is orbiting, or a different model where the shadow sort of oscillates around a particular position. There's currently an ongoing project to sort of fill in the sampling here, and that's going to really help us break the degeneracy between these two models. But in terms of looking at the gas, no matter what you assume about the movement of the shadow, we found that the gas shadow was always slightly lagging behind. So that's shown by this little black point here. So if we assume an oscillating shadow, it's only just offset. But if we assume a sort of a constant angular rotation, there's quite a substantial difference here. And this is really compelling because it's showing you that there's a delay between the shadow that we see in the scattered light, which should be almost instantaneous as it's light just scattering off the grains, and the gas, which requires a transfer of the energy from the grains, getting heated up, and then transferring that temperature to the gas itself. And this allowed us actually to calculate how efficiently coupled the dust and the gas were in this system. And we found that depending on the model you assume for the rotation period of the shadow, it was anywhere between 10 years and an almost instantaneous transfer of energy between these two components. And so again, this is not really a surprising result. This is exactly what we would expect from a disk, given the densities that we think they are. But it's really nice that we can actually test this empirically with these sort of measurements. We're no longer just relying on model assumptions. We can go out and use data to test that these things are the case. We can also look at the temperature structure in 2 dimensions. So I've focused with the shadows just at looking at temperature along the surface of the disk. But by using different isotope logs, different molecules that all arise from different locations in the disk, we can start to map out the temperature structure in 2 dimensions. So again, this is some work by Charles Law, where he applied this to 5 disks as part of the MAPS large program. So this was an ALMA large program led by Karen Oberg here to map the chemistry in these 5 sources. And Charles was able to come up with these sort of distributions, which again showed you the 2D temperature structure, which really well aligned with our theoretical predictions. So we're seeing a very hot surface of the disk, which is directly irradiated from that central star, and then a much cooler midplane, because we have this dust that's shielding that inner region from this radiation, and much colder temperatures down here. So by just studying the 3-dimensional structure of the disk, or looking at the distribution of the gas and dust in space, is really telling us a lot of crucial things and sort of valuable things that we need to input into our models. We have a way to look at the vertical density distribution, understanding how that gas is distributed at the midplane and further up in the atmosphere. We can look at things like the temperature distribution, how that varies, whether we have how cold the midplane is, or how strong that temperature gradient is. And we can also look for sort of warps or broken disks relative from the inside of the disk to the outside. And all of these are going to point to perhaps different dynamical processes that may be present in the disk and driving planet formation. So these have been really crucial in trying to understand what processes may be there, may be present, and may be driving planet formation, as I said. And I think for the last couple of decades, theoreticians have really had a field day in terms of dreaming up new hydrodynamical or magnetohydrodynamical processes that could be present in a protoplanetary disk, really because they've just not had any observational constraints on what could be there. And this figure is coming from a very recent review for the Protostars and Planets 7 review, looking at what various instabilities people have found. And this is trying to plot, as a function of radius in the disk, on the x-axis and height in the disk, which of these instabilities are likely going to be present or most active. And while we don't want to really go through all of these in particular, what I want to draw your attention to is that in the very inner regions of the disk, we have the MHD winds, the magnetohydrodynamical wind, or the magnetorotational instability, and you have the similar instabilities at the outer disk. And then this inner region, where we're finding a lot of planets between 1 and 100 AU, we're seeing a lot more hydro instabilities, so things that don't need a magnetic field. And so we've made a lot of progress here in trying to map these out, but we really don't have a good idea of whether we have the magnetic fields necessary to generate these sort of instabilities that we're saying are present in the very inner disk and in the very outer disk. And this is quite a surprising fact, I think, because we have really wonderful measurements of the magnetic field in our own solar system while that was very young. So this is work done by Roger Fu, who's over at the EPS department here in Harvard, or Ben Weiss at MIT. And they do these really fantastic experiments where they take meteors that have landed on Earth, they chop them up, and they look for ferromagnetic material within these meteorites. They can then measure the magnetic fields within these materials that are embedded within the meteorites, and looking at the relative field orientations, they can distinguish between a primordial magnetic field or some sort of secondary magnetization, then also place estimates on when that magnetization occurred and how far away from the star it must have occurred based on the materials in that meteorite. And so these sort of measurements are really allowing us to plot how the magnetic field changed in our solar system as a function of time. So planetary scientists typically measure time after CAI formation. So this is calcium aluminum inclusions. And this is basically the start of the solar system at time 0. And you can see that we start with a magnetic field of around 1 Gauss. Then over the next 4-5 million years, it drops to something like 1% of its previous value. So we've got really wonderful data, empirical data, showing you that we have magnetic fields in our own solar system, but we don't actually have any evidence that we have magnetic fields in protoplanetary disks, which is a really surprising fact. So this is primarily because the way that we've been trying to detect magnetic fields is through continuum polarization. And so this is just an example of it, these 2 figures showing you the polarization vectors for continuum around a young star, around TW Hydra. And it's thought that this polarization was tracing the magnetic fields because the grains were thought to align themselves along the magnetic field lines in the disk, and then because you have all the grains aligned in a preferential direction, that's going to give rise to polarization. However, when we started seeing all this different polarization, it was really exciting, but it turned out there's actually several different mechanisms that you can invoke to align those grains. There's nothing really that specifically says the alignment has to be by a magnetic field. We can think about something like radiative torques, moving those grains into a certain alignment, or something like a simple headwind. As these grains move through gas, that's going to turn them to a preferential direction. So really at the moment, we're not very confident in being able to see that any of the polarization that we're seeing from the continuum is actually due to the magnetic fields of the disk. So we need to think about a different approach. And the way that I've been trying to do it is to look at the molecular line polarization. So here, the magnetic field is thought to split the energy levels of the molecules that you're looking at in such a way that that splitting of the energy levels gives you linear polarization. And so we think we made last year the first detection of linear polarization from molecular line emission in a disk, which I'm showing you on the left. So the top panel is the unpolarized light that we're seeing, the total intensity, and this is actually the observation. So the error bars on this line are narrower than the line width here. So these are incredibly deep data. It's incredible. And then on the bottom, we're showing you the polarized emission. So the Stokes Q and U, the blue and red lines are linear polarization, and Stokes V is in gray. This is circular polarization. And you can see that around the line peak, we do make some detections of this emission. And you can see based on the scales, this is in millijanskis and this is in janskis. So it's an order of 10 to the 3 difference in how bright these things are. So this is an incredibly weak signal that we're seeing. But we think this is a detection of the Goldreich-Kalafis effect, and so suggesting that there is indeed a magnetic field in this system. This is really exciting because it suggests that perhaps we do have a way to detect magnetic fields in disks, but trying to get linear polarization is an incredibly challenging proposition. We've requested more time to go back and try and confirm these results, but that's going to take something like 25 hours on ALMA, and we're only going to do a factor of 2 better than this. So this is a very challenging sort of observation that takes a lot of time to pull out the signal. But an alternative method that we've been trying, and I'm really excited about, is to look instead for the Zeeman splitting of the lines. So this is a very similar phenomenon where the magnetic field is splitting the magnetic sublevels of these molecules. And this means that when you look at a line that's actually the superposition of multiple magnetic sublevels, when that field is applied to it, they will split apart and broaden the line that you're seeing. So if you can measure a line being broadened because of this, then you can infer the magnetic field that is incident on that molecule. And the real power with this technique, firstly, is that you don't need to look at polarized emission. This makes things a lot easier to calibrate. It's a much more direct observation. And secondly, we know from sort of understanding of molecular structure how sensitive each line is to the magnetic field. So these are just 3 example lines from a CN transition. And you can see because they have different sensitivities to the magnetic field, you see different amounts of broadening between each one. So for the rotational state of CN, we have 14 of these that we can observe simultaneously. And so we have 14 chances to detect this broadening. And the fact that each of the lines has a separate dependence on the magnetic field means that we can very easily distinguish magnetic fields from any other sort of systematic effects of broadening, either instrumental or physical reasoning. So I'm really excited about this. We've got another ALMA program going to try and get this. This is another sort of 30 hours integrating down to try and measure this broadening. But we should be able to get a sensitivity of 10 milligauss at a 5 sigma level across the disk. So this should be comparable to the sort of magnetic fields that we've expected the solar system have at those same sort of radii. And I'm really excited to see where those observations take us. If we do detect sort of broadening in the system, there's a second step which is sort of really powerful as well. And that's that the broadening is dependent on the line of sight component, so how the magnetic field is projected along your line of sight. As I argued earlier, we know very well the orientation of these disks on the sky. So if we have models of the magnetic field, whether it's a poloidal field or a toroidal field, we know how that line of sight component changes across the disk. And so by comparing how the broadening changes across the surface of the disk, we're actually also going to be able to get a 3D structure of the morphology of the magnetic field as well as the strength. So in one fell swoop, we're going to be able to go from a situation where we don't have any idea about the magnetic field to hopefully having a 3D magnetic field structure and strength there. And that's going to be really important for sort of understanding which of these magnetohydrodynamical processes could be present in a disk and driving the planet formation process. So of course, there's lots of other things that you can do with molecules. It's not just looking for Zeeman splitting. As I mentioned earlier, Karen Oberg led the MAPS large program, where we were surveying 5 disks and looking at the chemical complexity in these. And this is just a gallery for one disk, HD 163296, and just a sample of the molecules that we detected in it. And what I really want you to take away from these images is that even though this is the same disk, different molecules have completely different spatial morphologies. You're seeing some, like H2CO, which are very extended and broad emission, and you're seeing others like the C2H, which is very sort of well-defined 2 different rings. So there's a huge amount of structure in there. And if we understand what conditions these molecules thrive in terms of temperatures and densities, then understanding the difference in morphologies is going to be a very powerful tool to improving our understanding of what the physical conditions are in these disks. And so this is something that I'm really interested in pursuing, and with the MAPS data, we just have a whole load of data to play with to try and make sense of. The thing that I really like about lines is, rather than looking at the chemistry, is that we can start to look at the kinematics of them. And so with something like ALMA, we can really achieve incredible spectral resolutions such that you're really understanding the entire line profile shape. We're no longer in a case where we're getting a few samples across the line, but we can measure this at down to something like 13 meters per second. So the full width half maximum of these lines is around about 250 meters per second, and the spectral resolutions are a factor of 10 better than that. So we're really going to see how these lines look and see if there's any subtle deviations that can tell us about the kinematics of these disks. So over the last couple of years, we've started amassing a huge amount of data looking at these molecular lines and disks, and we've started to look at the sort of dynamical structure of them. So this is work done by Lisa Wolfer, who's a recent graduate of Leiden University, and she went to the ALMA archive and looked for every single disk that has CO emission and tried to understand what the dynamical structure is. So you can see all of these disks have lots of different complexities going on. There's some that are a bit noisy and there's not a lot you can really do with them, but by and large, all of them have this sort of dipolar morphology of a rotating disk. You can see, those of you with keen eyes, that many of them have this bending in the dipole morphology. And that's really down to this 3D structure that I was telling you about. So if this was a flat disk, these dipolar components would be directly reflected. But because you have this 3D surface that we're tracing, this actually bends those isovelocity contours. And so we're really starting to see that 3D structure. And this is why it's been sort of a hindrance, because we've now got to take this into account in all our analyses. The flip side of it, though, is that while we can see the front side of the disk, we can also see the back side of the disk. So this is work that I'm doing with Carlos Muñoz Romero, who is a graduate student here as well. And here we're looking at trying to understand how we can decompose this data and look at the front side of the disk and the back side at the same time. And so these are results from some of his work where we've managed to take data from this MAPS large program and constrain the surface on the front of the disk and the back side at the same time. And this is going to allow us to study the velocity structure on 2 sides of the disk, which is going to let us look for deviations and see whether they're reflected about the midplane. So if the source was something coming from the midplane like a planet, it should have reflected velocities. Or if the velocity structures that we see look like they just cross over the midplane and are across the whole disk. This is going to be a really powerful way for us to distinguish between those whole slew of dynamical processes that I showed you earlier. As with the magnetic field, though, we can also think about how we want to decompose that line of sight velocity into its constituent components. And we've also been able to do this. So this is an example for a HD 163296, where we decompose the line of sight velocity into its rotational, radial, and vertical components. And this is just plotting the velocities we get for the radial and vertical components as sort of a cross-section through the disk. So the arc that you're seeing is that emission surface that we were able to extract. And these arrows are showing you the velocity structure that we measured from the data. And you can see that there's really quite a lot of structure going on here. you see these three regions of collapsing flows, or meridional flows, and these align nicely with gaps that we've already observed in the disk in the continuum. And what we think we're seeing here is flows at the edge of these gaps trying to fill in those gaps that have been potentially opened by planets, and the material from the atmosphere is coming down and flowing like waterfalls to try and close those gaps. We also see in the outer edge of the disk this sort of persistent radial outflow, which we think is the base of a disk wind. So we know in this system there's a large-scale disk wind over thousands of AU and a really strong jet, and we think that these velocities are sort of tracing the very base of that. And if this is true, this is going to really give us the first opportunity to understand how these winds are launched in practice. So going back to that diagram of different instabilities, this would be looking at whether we have a photoevaporative wind or a magneto-hydrodynamical wind. So this is really fantastic. We sort of moved in the last 5 years from thinking of a disk as just rotating in purely Keplerian rotation to being able to look at the front and the back side of the disk and to decompose those velocities into the 3D cardinal components. But of course, this has all assumed that things are azimuthally symmetric. And we want to see if there's any subtle perturbations in the disk. And so when we look at the Keplerian rotation, we think it's going to be dominated just by that gravitational component moving it around the star. So if we model that Keplerian component just with a single stellar mass and then a simple 1 over r squared law, we can subtract that away from the disk, from the observed rotation velocity, and we're left with these sort of stunning residuals here. So this is a bit messy. You can see up here at the top we have very large residuals. That's because we're actually tracing the backside of the disk here. You can imagine that if you have a cylinder and you've tilted it towards me, that top edge of it is going to be the backside that you're seeing. But on the front side, you're seeing these really strong spiral-like structures here extending all the way around the disk, and we're seeing lots of arc-like structures as well. And these are fairly large velocity perturbations, so you can see these are up close to 100 meters per second. And as I was saying, the velocity resolution of this sort of data is down at 20, 30 meters per second. So these are really significant deviations that we're seeing. And this is not something that we're seeing in just one disk or two disks, but nearly every disk that we look at, again with enough detail, similar to the continuum substructure, we're seeing a tremendous amount of velocity structure there as well. And we think really this is hopefully down to embedded planets. So these are just some examples of some simulations we ran. Where on the left, we started off with a smooth disk and injected 3 different planets into there with different masses. And you can see, as you'd expect, the planets open up gaps around them at their orbital radius, and they also drive these spiral wakes where they're shocking the gas. When you look at how they impact the rotation velocity of the gas, which is what I'm showing you in the center here, you can see that they drive a huge amount of change. So here the units are sort of plus or minus 5% of Keplerian rotation. So this is really quite a large variation that we're seeing. And the features really consist of these large annular features at the edges of the gaps. But also around the planets themselves, we see these spiral wakes really shine brightly in sort of velocity deviation. And what's particularly powerful about this mechanism is that while in the density you can't really tell where the planet is unless you have really exquisite resolution, the fact that the velocity deviations flip sign on either side of the planet means that this is a very powerful way to find where the planet is when you're looking at these sort of maps. And so when we look in our data, we think we're starting to see these spiral wakes around the planets. When we look at this radio data, we essentially look at the emission for a fixed frequency or velocity offset. Because we know the emission is sort of governed by the Doppler shift of the gas, any localized deviation in the emission for a set frequency or velocity is going to then be related to a localized deviation in velocity. So this was some work that Christoph Punt did, where he was looking at emission from HD 163296. And on this left image, this particular velocity, he noticed this very striking, what he called a velocity kink feature, sort of thunderbolt pattern in the emission distribution. When he looked at the other side of the disk here, you could see that it was very smooth, and so it didn't seem like there was any deviation here, but you definitely needed something in the disk to cause that feature. And when he moved to the other side of the disk, so looking at a different velocity, you can see that again, everything looks nice and smooth. So the way that he could explain this localized deviation is that you needed a planet almost directly north of the star, and these breaks, this kink, is caused by these spiral wakes of the planet, shifting that emission away from it locally to the planet. And so we've been able to see this really nicely in HD 163296. Christoph found a second one in a different disk. And more recently, there's been this really nice detection by Jehan Bey of a similar feature in AS209. And so on the left, we're showing you the 12CO emission. And again, you can see, hopefully, this very large kink that we're seeing. So on the north side, this is nice and straight. But on the southern side, you have this very large break here, which means there must be a very large velocity perturbation around that location. And when Jehan explored the data that we had a little bit more and went to look at 13CO, which is a slightly less abundant molecule and so should be tracing closer to the midplane in the disk, he found that there was a point source exactly in the middle of this velocity kink. So what we think we've detected here is actually the circumplanetary disk around the planetary perturber that's driving those large velocity perturbations that we see in the 12CO. So we know already that there's a large gap at this location, there's a very large velocity perturbation, and there's a point source at the center of that gap. So we're very confident that what we're seeing here is likely a planet, and it's going to be somewhere between a Saturn mass and a Jupiter mass planet. And I think these sort of observations are really going to become a lot more commonplace as we get more and more data. This doesn't always work, though, if your disk is face-on. So just by the orientation of the disk, if you're looking at something that's face-on, the projected velocities are going to be much harder to see. But also, if you want to try and follow up these objects with direct imaging, face-on disks are going to be the best for this because you're going to minimize that column of material you need to look for to find that planet. And so with TW Hydra, which is the face-on disk, we're starting to try and do the same sort of analyses and identify where the planets may be. So I'm showing here distributions of the dust. So on the left, we've got these submicron grains high up in the atmosphere taken with sphere. And you can see that there's lots of rings and gaps there. And on the right, I'm showing you the continuum emission, so tracing these larger grains closer to the midplane, and these are sort of concentrated in the inner regions of the disk. But again, in the millimeter grains, we're seeing these very narrow, well-defined rings. And so there's quite a lot of evidence for planets just based on the dust. But even when we look to molecular emission, we can see that there's gaps at similar locations. So at 90 AU from the star, we really have this massive gap that we see not only in the dust, but also in the gas distribution. So we really think there had to be something there that was driving that gap. And when we went to go look at the velocity structure of the disk, we found these really wonderful sort of spiral kinematic features in there. So the left panel is showing you the original data that we had. This was archival data at 345 gigahertz. And at the location of the gap, shown by this dotted ring here, and you can see on the right how that relates to the scattered light, we found this very tightly wound spiral arc location that coincided with the gap location. And this was really intriguing. We thought this had to be the sign of an embedded planet. So we went back to ALMA to ask for some DTT time to follow this up, and we got this slightly lower frequency data. And here, with observations designed to do this sort of work, we found this really wonderful spiral pattern emanating from the disk. And so what we think we're seeing here is a young embedded planet that's carving out this gap around here. And then we're seeing something like a blue shifted component here and a red shifted component here, sort of accounting for that sign flip that I showed you in the models before. And so we can work with simple analytical models of what a planet should do to try and estimate the mass of the planet that you need to drive these sort of perturbations. So these aren't excellent fits to the data. These are obviously very simple analytical models, but just looking at the magnitude of the deviations that we're driving, we could see that to get the sort of close to 100 meters per second deviation, we need something around a Saturn mass planet to do this. So by comparing the dust distributions, the molecular line distributions, and the kinematics that we see, we're fairly confident that in this disk there has to be a Saturn mass planet all the way out at 90 AU that's carving that gap. And so this is hopefully a target that we're going to get observed as part of one of the GTO programs for James Webb. And so we're really excited to see if they detect anything in this particular source. So with these sort of observations, I think we're opening up a new area of parameter space. So these orange points, these stars, are showing you planets that we think we've detected based on the kinematics that we're tracing with ALMA, and lots of other potential candidates that we need to follow up and sort of get better observations for. And you can see that we're really pushing out into the much wider separation planets and also the more massive ones. But I think the real important dimension that we're pushing here is time. This is something that we're not seeing on the figure. These orange points are all a few million years old, so right at the very start of their formation, whereas everything else on this figure in the gray and black is sort of fully formed, mature systems that are much, much older. And so it's only by looking at these orange points, these young sources, are we really going to understand that planet formation process. And so that's really the goal of this EXO-ALMA program that I'm leading. So this is another large program with ALMA, where we're surveying 15 disks to try and find these signatures of embedded, still-forming exoplanets. So I'm leading this along with Miriam Benesty, Stefano Fucini, Mizuto Fukugawa, and Christoph Punt. And we've really got an excellent team of students and postdocs and researchers working with us to make the data sort of the best it can be from the telescope, and really applying sort of novel methodologies to try and extract these disks, these planets from these disks. So the data is still coming in. I think we've got a few more weeks of data collection, and then the whole team should be descending on Cambridge in December to start playing with the data and analyzing it. But these are just a few of the sort of sources that we're looking at here. So you can see we have these weird donut-shaped things in here. It's hard to tell on the projector, but there's a large spiral in there. And the one on the left is also showing lots of sort of spiral structured arms around it. So there's lots of features in this data, and I'm really excited to see what we're going to be able to say from that sort of data. So to just conclude, I think that we are well on our way to developing a 6-dimensional view of the planet formation process. I don't think we're completely there, but we are definitely on the way to getting the observations that we need, and we're developing the tools and methodologies that we need to analyze them. So in particular, we're able to survey all these disks and look at the dust distribution, and we're seeing these wonderful gaps and rings to have an understanding of how the planets are shepherding the grains around these young stars. We can also look at the velocity perturbations within these systems. We can see whether we can identify where the planets are based on these very localized spiral wakes that they're forming. And then around those planets, we can also look at the 3D velocity structure in the vertical dimension to understand how material is being transported perhaps from the atmosphere of these disks down to these young planets to form their atmospheres. So this talk is really focused on ALMA. I think this has really been the instrument or the facility that's been making a lot of progress in this. But the future is incredibly bright. We now have James Webb up and running. That's going to provide a tremendous amount of data looking for accreting planets. The NGVLA is on the horizon. This is going to allow us to push these techniques into the terrestrial planet forming region. And the ELTs are also going to be fantastic here, where there's a lot of stuff that we're going to be able to do in the inner disk, particularly in the mid-infrared and infrared, that we simply haven't been able to do before. So I'm really excited to see where that goes. And so with that, I'd like to thank you for your attention, and I'd be happy to take any questions.
Well, that was a fascinating talk, and I'm sure there's a lot of questions. Already one over there, Randall.
You had that interesting graph figure showing all the different molecules that you've seen besides just CO.
Yeah.
Showing lots of different morphologies.
Yeah.
Are you thinking that what you're seeing there is different in formation of those molecules, or differences in how they disperse after they're formed?
It's going to be the formation. It's going to be what conditions they thrive best in terms of temperatures and densities. There's probably going to be some feedback from sort of radiation processes, so if they need ionization, say to form regions where you have higher ionization, but it's really going to be the formation and destruction mechanisms that's controlling their distribution rather than any sort of dispersal.
And then the obvious follow-up of that is that, especially for rocky planets where the core is even possibly a gas giant, it's going to be heavier metals, the silicates and so on, that you just unfortunately can't see.
Yeah.
Is there any way to trace what those might be doing from the information that you have to know how the cores, how rocky planets might form or how cores might form?
So that's a really tough thing to do. We can only really look at the gas components here. You can look at sort of maybe the mineralogy of the dust in these disks, but that's such a degenerate problem. It's very hard to really get a handle on what's going on there. I think we have to look at sort of the ISM dust and assume that that's the same all the way down, essentially. Yeah, that's going to be a tough problem to solve.
Yes.
You mentioned the flares in the planetary disks. What is the cause of these flares?
The flares?
Yes.
So it's essentially the flares we think are just from accretion onto the central star. So when the disks dump material on there, they release a tremendous amount of energy, and then we get those flares. And so we've actually seen that not only in the brightening of the stars, but there's also been some work by Ilse Cleves that has shown that the ionization structure of the disk actually is enhanced for a little while after these flares, and then it dies back down to a steady state. That's a really interesting sort of time domain aspect of this that I didn't touch upon.
Got a question online?
Just your request to repeat the question.
No.
Oh. Yes.
So, this is amazing stuff. You didn't explain how you're doing all of these inversions from the data. And I'm trying to visualize. So certainly if I take a bagel and tilt it and look at it, and if I assume it's axisymmetric, I can imagine getting the third dimension. And I think that's all what you are doing. And I was happy. And then suddenly you said, oh, but really it's not axisymmetric. I'm also going to pull out the non-axisymmetric structure. So then I got a little, can you really do all of that from the same 2D data?
Okay, So the question was, part of the analysis that I showed required us to assume axis symmetry, but then I showed that these things aren't axis symmetric. So how do we reconcile those two components? And the honest answer is that's what we're trying to figure out how to do now. We started off thinking they're all axis symmetric, and it worked very nicely, and now we're seeing all this structure. And this is something we have to deal with. We're trying to understand how big of an issue that is. I think in terms of, say, the 3D structure, that's probably not going to be an issue. There's one disk where people have claimed that there's a difference, so one side is thicker than the other. But in most of the sources that we've seen, they appear to be broadly axis symmetric, and it's just the velocity perturbations that aren't. And so these perturbations, while they're significant detections, they are only sort of minor perturbations in the grand scheme of things. They're sort of tens to 100 meters per second deviations that we don't think are going to bias our observations that much. But this is definitely something to work on as part of this EXO-ALMA program, is to quantify that to make sure this is robust.
Okay, yes.
You separated the front surface from the back surface.
Yeah.
Do you do that with different isotopes, so you have different depths you're seeing?
So that's part of it, but essentially what we're doing is we now have this, so the question is how do we disentangle the front and the back side of the disk? And that's essentially that we can just see when these disks are sort of inclined along our line of sight, we can actually see the back side of the disk. Let me try and find a picture that shows you that. So this shows you quite well. I think it's a bit bright, but if you were to look at this image here, is it possible to dim the lights briefly? Yeah, thank you. So you can just about make out that this sort of bright arc represents the front, and then if you can just see there's a fainter arc in the background here, and so we can spatially resolve that. We can attribute that to the backside of the disk directly.
Okay,
Yeah.
2 more questions. We're running out of time. Yes.
Yeah, on your last class, the new detections of forming exoplanets and candidates, they seem to be at larger radius than the others.
Yeah.
Is this due to the method, or is it due to their age?
Yeah, so the question is, why do we seem to be having all these planets at very large radii? Essentially, this is just an angular resolution issue. With ALMA, we're sort of having angular resolutions of down to 10 AU, so we can't push much that direction. But there is scope to do this. ALMA can go a little bit deeper. But I think also trying to look at how we apply these techniques, say with zero-row vibrational lines. So that's something I'm really interested in, looking at whether the ELT can look at zero-row vibrational lines and push these techniques to those inner regions. That's a way to make that connection. But at the moment, we're just limited by ALMA.
Okay, last question, Andrew.
You mentioned that time is yet another dimension. Now, one of those targets, TW Haya, we've been looking at for decades, perhaps. Have you seen any changes? Have you seen the motion of those putative planets?
Yeah, so the question is, have we seen any time dependence on TW Hydra? In terms of planets, no, because we haven't been looking with that much detail. But we've definitely seen the shadow moving. So the shadow moves quite a lot on the surface. And so it looks like if that's being cast by something in the inner disk, that would have a very short period, on the order of a few years. But we don't really have the time baselines to look at those planets. Again, that's something that NGVLA should be able to do, but not with ALMA quite yet.
Okay, thanks very much. Please join me in thanking each of the